Alright everyone, welcome back to the day 52 of our daily leetcode challenge, and today we have got find elements in a contaminated binary tree. So in this question is basically divided in two parts. What they have provided us with is a binary tree which is initially contaminated. So since this tree is now contaminated, first what we need to do is, our step 1 would be to recover back this tree. First is to recover back this tree. And once this tree is recovered, we need to find if certain list of elements are present in this tree or not. So that's the easy part. First part is the recovery and the second part is finding of elements. So initially they will be providing us with a contaminated tree which will be looking like this. All elements will be set to -1. All elements will be set to -1 in the tree. At all roots and at all leaves, you'll see that the values are -1. So the step 1 is to recover the tree back. So how do we going to recover it? They have provided us with a rule here. If you see, if the value of the node, if the value of a node is not null, and if you assume its value as x, then for this node, if the left node exists, then if the right node exists, this is the right node and this is the left node, which is empty in this case. But if the right node exists for a node for whose value is x, the value of the right node is going to be 2 times x plus 2, which you can see is written here. If tree node dot val has a value, which means if this node, a particular node has value, and the right node is not null, then the value of the right node will be 2 times of the value of the parent plus 2, and the value of the left node will be 2 times the value of the parent plus 1. So this will be 2 times x plus 1. So if you and the another thing to note is that the value of the root will always be 0. So out of the contaminated tree, which initially will look like this, all values as -1, even if you forget everything, just note that the value of the root node will always be 0. The value of the root node will always be 0, and using this root node we can build back the tree using the rule that they have provided. So if this is our current node which you are currently at, they said that if this node is not null, assume its value as x. So if the value of this current node, parent node, is x, and the right node and the left node are not null, the right node here is not null and the left node here is not null. Not null meaning the node exists. If that's the case, then the value of the right node will always be 2 times the parent nodes plus 2, and the left node will be 2 times the value of parent node plus 1. And then this same thing will continue forward. For this node right here, this is the leaf node. We don't have any more nodes out here, so we'll have to terminate the loop here, because for the left and the right for this node is a null node, doesn't exist. But for this step right here, for this left node, we have 2 more nodes as its child, left and right. So for this one, again the same formula will apply. Right now our x value is 2 times x plus 1. Now for this node right here, this is the parent node and these are the left and right nodes for this. So for the right node right here, the value will be 2 times of this value right here, 2 times of 2x plus 1 plus 2, and in this case it will be 2 times 2x plus 1 plus 1, since this is the left node. So since we started at a 0, we can build down this tree. We can build down this entire tree using the formula that they have given. So let's try to build that up. Let's take the first example. In the first example, the tree looks like this. It is -1 as the parent node, and then -1 as the right node. Left node doesn't exist. So they have clearly mentioned that the right node will always be a 0. So this will be a 0. Now since this is a 0, means this is our x. So using this formula, the right value, the right node will be, if this is our x right now, the right node will be 2 times of x, which is 0 plus 2, since this is the right node and it exists. It's a -1 here, it means the node existed. So this will now turn out to be a 2. So that is why this tree now recovered looks like this: -1, 2, a 0, and the right node value as 2. So this is for the first one, which is a simple one. Now let's try to do the same thing for the second tree. The second tree looks like this. We have a -1 at the top, which is the root node. This root node has 2 children, left and right, both value as -1, because initially the tree is contaminated, all values are -1. We need to first recover the tree. That is the major step. If you are able to do that, this question clearly becomes an easy problem. Once you are able to recover this tree, this question will become an easy problem. So I'll tell you why. So now we have this tree. Again, the root node will always be 0. The root node will always be 0. So let's make that this is our root node, all its and its value is 0. Now again in the formula it's mentioned, if the right node exists, meaning the right node is not null, then the value of the right node will become 2 times the value of the parent plus 2. So this will be 2 times of 0 plus 2, which will be 2 again, just like we saw in the previous example. And for the left node, it will be 2 times the parent, which is 0 plus 1. So this will become now 1. Now for this level right here, which we are now, and now the same process will go for these two nodes. The same thing we did for this node was what we're going to do for these two nodes. Now this becomes the parent. Since this is a parent, it doesn't have any child node, so we will terminate for this one. We'll terminate. But for this one, it has two child, left and right. So we'll do the same process for this node now. Assume this as the parent, and then find the values for its left and right nodes, child nodes. So the right node will be 2 times the value of parent, which will be 2 times into 1, which will be 2, and then plus 2. So this gives us 4. So this node right here has a value 4. And for the left node, which will be 2 times the parent plus 1. So that will become 3. So that is why for the left node, it's 3. So now we have recovered our tree. This is how we are recovering the tree using the formula. We start at the root node, and then from there on we do a build up. We start building. So we are going left and then right. For each node we find its value of its root, replace that with 0, and from there on we build. We started with the 0, and this is how we build the tree. So if you see for the second example, this is how our tree looks like: 0, 1, 2, 3, 4. We have got the tree. Now since we have got the tree, we can clearly tell if the values that they have provided here, 1, 3, 5, these values are there in the tree or not. Since 1 is present in the 3, so it's a true. 3 is present in the tree, so it's a true again. But 5 is not present in the tree, so it's a false. So this is how the question is working. First step is to always rebuild the tree. First step will be to rebuild the tree, and the second step will be to find all these values if they are present or not. So again, since this operation right here is going to happen only after our tree is recovered, so it's better to keep a track of all the values that we'll be finding for each node of this tree and storing it somewhere. So what I mean by that is at each step that we are here right now, while we were kind of recovering the tree, at this point we were recovering the tree. At each node that is getting recovered, whatever value we are obtaining by this formula, 2 times of x plus 1 or plus 2 for the left and right node, what we can do is we can store all this value by the formula that we are getting to a set. We'll declare a set, and in this set, as and when we are recovering this tree step by step, we'll keep storing these recovered values in a set, so that once the entire tree is recovered, what we are left with a set of all the nodes and its values. Basically the value of all the nodes that they were present in the tree, the recovered tree. We'll have a set of all the values. Now once this step is done, which is the find elements one, once this call is done, this will now become an easy problem, because all we need to do is find if a particular value is present in this set or not, which will be done using the second function that they have provided here. This is the second function. We'll code this up and I'll explain you how we are doing this. So this is how the algorithm is going to work. First step is to recover the tree. So now to recover this tree, what we're going to do is we're going to use a depth first search, DFS. So DFS will be our helper function. We'll define this function. We'll start with the root node, and with this root node we'll keep on going to the bottom of the tree by, again, first we'll start with the root node. So the function, recursive function, will look something like this. We will define our DFS method inside the init method that they have provided and name it as DFS. It will start with a node. Initially this node will be root node. So we'll do the operation for that root node, and from there on we'll go to the node.left and node.right. So for that, again, this DFS will be called on its left and right child, node.left and node.right. This is how the DFS functions work. And before we call these functions on the left and right child, we'll have to also make sure that we also may introduce a case where we'll have to terminate this DFS. So what I mean by that is, if the node is not null, we realized in the previous example that when we reach the case when the node didn't had any left or right child, we had terminated that formulation that we did. So when we are going to terminate for a node this formulation, because for the right node we are going to do if the node exists, but for the left node we won't do if the node doesn't exist. So basically if the node doesn't exist, there's no need to do a DFS. So that's where the base case will exist, and we'll slightly alter this method to kind of find the values, and then as the value is found, we'll store that in a set. As we'll code this up, you will get to understand this better. So let's try to code up the first part, which is recovering the tree. So this step is to recover the tree using simple DFS. DFS is nothing but a depth first search. We are iterating this entire tree basically. We are iterating from top to bottom, and with each iteration we are checking if the value is a root node, replace it with a 0, and once that is done, we go to the left and right node, and if the left and right node exist, we apply the formulation that we have provided us, and then as long as we are kind of iterating through each of the nodes, we store those values in a set. So as we said, we have to declare a set as well, so that in this set we keep a track of all the values that this recovered binary tree has. So as you can see, this recovered binary tree has 0, 1, 2, 3, 4. We'll create a set called self.set1, and in this set we're gonna keep adding the recovered values of each of the nodes that we traversed. So when we are at the root node, we know the root node is gonna always be 0, so we'll add a 0. Now comes the question, how are we gonna know that the root node, like at a particular node, like when we start with, how we gonna know this node is a root node? So initially when we first call the function DFS function, the first node is gonna be a root node, but all the nodes after that will be the child node. So to kind of make this obvious, what we can do is set a flag to true, so that when the very first time our DFS function is called, that will be called for our root node, and in that case the value of the flag will be true. Only then we will be aware that alright, this node that we are currently at is a root node, because the first DFS will be called on the root node itself. The first time we'll be calling a DFS will be called on the root node. That then and only then the flag will be true. Once the root node evaluation is done, we'll set this flag to false, so that all the upcoming nodes, for them the value will be set to false, and we don't we will know that those nodes are not the root nodes, because we need to know which one node is the root node, so that we can set its value to 0 specifically, because the root node will always be 0, and once this 0 is found, all the values here on can be found as well, which using the formula that they have provided. So now let's try to define a DFS function. So this is our DFS function right here. The reason we have put a self keyword here, so that these two variables can be accessed throughout. These two variables that we have declared, set1 and flag, will be not only be accessible in this function. In this function we could access them, but also in this separate method that we have defined here, this method here can also have access to this set1, which will be required to find each of these elements are present in this set or not, which will be our second step, the easy step. So let's try to declare our DFS now. So first, as I said, we need to know when to terminate this entire DFS. So if the node that this DFS takes doesn't exist, that's when we need to terminate our DFS. This is our base case. We should always declare our base case whenever we are defining our DFS, so that we know when to stop. So if not node, basically this basically means node doesn't exist, then we can simply return. This would mean do nothing, terminate the loop. Now the loop gets terminated here, the DFS gets terminated here. Now comes the case, how will we know if the node value, this node is a root node? So since we know that the first time the DFS will be called, the flag will be true, and also the value of that node will be 0, so it will be -1, sorry. So if node.val is equal to -1 and flag self.flag, we'll have to access via this self.flag is true. This basically means this is true. If that's the case, we know we are dealing with the root node. In that case, what we have to do is, first step is to update the value of this to a 0, because that's how we know this node is no ordinary node, this is a root node, so the value becomes 0. That's one. And once that is done, what we need to do is, in this set self.set1, we'll have to add 0, because this is our root node. We just recovered our root node and set its value to 0. We need to add this to our set so that we keep track of all the values. And once this is done, we'll have to set the flag to false so that no other values are confused as the root node. This if condition is only for the root node itself. So now the root node is dealt with. What we need to do is check if the left and the right node exist for a particular node. Now if the left node exists, right, if the left node exists for a node, so now this if condition will be taken care only if the node dot value is -1 and self dot flag is true, meaning the case of root node. This is the case of root node. This is dealt with, and if the condition doesn't go in this one and this one, that would mean that those nodes are the intermediate nodes, meaning the nodes other than the root node. So if that's the case, so in this case of 1 we have, so if 1 exists, if 1 exists, then for this node, if its left node exists, in that case what we need to do is set the value of node dot left from -1 to the new value, which will be node dot left new value will be whatever the parent is, which will be node dot val. We have to 2 times it and then add a +1. So node dot left dot val becomes this. Now this is the new value, and this new value has to be added to the set as well. Now we can add it. So that's just at this moment we updated the value. So this we did for the left part. Now again we need to do for the right part. Only if the node dot right exists. So if that happens, node dot right dot val will become 2 times node dot val plus 2, whatever is the value of the parent plus 2 to it. And then again we have to add this newly recovered value back to the set. Every time we are using the set, we'll have to call the self keyword, otherwise it will give us an error. In this set we'll have to add this new value that we just made. Now all the values are added. Now again what we need to do is we need to now call our recursive part, which is calling this method again on the left and the right node, parent node, the child node basically. If they don't exist, the loop will terminate. I don't mean the loop, the DFS method will terminate, and if that's not the case, it will go in either this one or this one or this one accordingly. So that's how the DFS is defined. Now what we need to do is call this DFS on our root node. Just now we defined our DFS. Now we need to call the DFS on the root node. So this is the step where we recovered the tree. Now our tree is recovered once this method is ran. Once this method runs, our entire tree will be recovered. Now once we have that, for this method, the second was we simply need to return if the target is present in self dot set 1. This is what it means. Target in self dot set 1. Return true or false if the particular value is present in this set or not. This exact set that we have been maintaining so far. So the reason we are adding a 0 here, because again this is the case for a root node. We know how this is a root node because the flag is initially true. When the root node is initially called, this will straight up go to this one. This is the first thing it will go to, because value is -1 and flag is set to true. Once this is done, 0 is added to the set. What will happen is the flag will set to false, and then it will go to its left and right child. If it exists, then the left and right child will be updated according to the values that there are, and then again this entire DFS will be continued on the left and right side. If they exist, it's fine, otherwise it will end using this return. So this is how we are recovering the tree, and once the tree is recovered, while we were recovering it, we were also maintaining a value of all the value in the tree in this set called set 1, and in the end we are just returning if that value that they are asking is present in this set or not. So let's try to run it now. So as you can see, it's satisfying all the test cases. Let's try to submit this now. So that's pretty much it. This is it for today. It takes 8 milliseconds and reached almost half the solutions that they have submitted. So yeah, that was it for today everyone. I'll see you in the next one. Like and subscribe. Bye.